Do it very slowly and asymptotically approach. That is the right word, asymptotically approach one. So if you put 1 here, so this function will start raising like this and approach. Okay, so this is the nature of the CDF. So what it will tell you is the probability of the lifetime. That is, you take a bulb and then look at the lifetime. It is exponentially distributed. So it will be lifetime will be like this one. What it again means is at this time, if you ask what is the probability that the bulb will fail, okay, in 3 months, 2 days, from between 9 o'clock to 10 o'clock, then what you do? This is 3 months, 2 days, 9 o'clock, 10 o'clock. So that 1 hour interval, if you want to find the probability of failure of the bulb, so you have to multiply the density function with the interval. That is the interpretation. So initially it has probability of more failures in small interval, and it goes, it decays and so on. That is the failure. The probability it will fail in an interval. As the interval changes, it changes. But what this tells you is, what is the probability that its lifetime is less than or equal to a given value? That probability is small. That is probability that it will fail if you start using a bulb for which 5-year warranty is given. What is the probability it will fail in a day? That is very less. What is the probability it will fail in 5 years? That will be considerable, 80%, 90%, that's how we look. As you take, what is the probability it will survive? It will fail within 100 years. That is will be almost 1.999. That's what it means. It is probability of the lifetime less than or equal to a given value. That probability increases slowly to 1 as x increases. Again, what will be the role of two different values of the parameter? So let's again same thing, lambda 1 greater than lambda 2. Then as you see, this one lambda 1 starts decaying, this one faster from higher point, it starts decaying faster as compared to lambda 2. So if this is lambda 2, lambda 1 will be of this form. So that is the CD. Then comes the expectation. So E of x. Again for continuous value random variable, start from the standard formula and then plug in the corresponding density function and then evaluate. So integral you can start from 0 plus infinity x into, this one is lambda e power of minus lambda x dx. So we will take a lambda outside, 0 to infinity, x into e power of minus lambda x dx. So to find this one, you will do it by parts, integration by parts. So I will conventionally will call this as the function u, and this can be have to be written as d of e power of minus lambda x by lambda. Am I right? So if I differentiate it, this minus minus gets cancelled, one lambda will come here, that will get cancelled, and then dx will come. That will not, this is what will happen. So lambda into, so the usual one, that will be that. U times b to the this one, u is nu x into e power minus lambda x with a minus sign here by lambda between 0 to infinity minus of again 0 to infinity and then v into du. Minus e power minus lambda x by lambda into dx. That's all what we get. So, if you look at this one, what will be the value of this? Entire thing. It has to be 0. If you put infinity here, this is infinity, but here it becomes minus infinity. When you put 0, that's no problem as such. You put 0, this becomes 0, and this becomes 1, so it is 0, definitely. But when you put infinity, is it definitely 0 or it is more than? Why? Huh? Yeah, that the other way of is that one is, this is infinity, but it is e power of minus 1, this decays faster than this. So the limit should be such that it should be 0. So it is 0 only, the entire function is lambda. So here minus minus plus and this lambda also comes out. So this goes away and then so what did we get? You get here, this is 0. Okay. Now minus sign is there, 0, and then if you put 0, you get, of course, okay. So what we find is 1 over lambda. So the expectation of a exponentially distributed random variable is the inverse of its parameter. So this is something which we have to clearly understand. So larger the value of lambda, the lesser its lifetime. Because larger the value of lambda, the lifetime decreases faster. So the expected lifetime is smaller. Smaller the value of lambda, the lifetime is slowly, it doesn't decay this one, so its expectation shifts. You can see that the expectation will shift. For lambda 1 it will be here, lambda 2, lambda 3 will shift like this. So this is then variance of x. So the first thing is second moment we have to find out as usual. So it is 0 to infinity. You can start putting 0 to infinity. X squared into lambda e power minus lambda x dx. Again we have to do by parts only. Twice we have to do. So lambda we will take it out. So first thing is x squared. As usual it is d of minus e power minus lambda x by lambda. This is how we will treat it. So x squared into minus e power minus lambda x by lambda between 0 to infinity minus of, so 2x into Well, this term becomes 0 always. Okay, x squared is the minus lambda x. Usually what will happen, even if you integrate many times, all the time this will keep becoming 0. You know, in the sense that you start from x power 5 and so on, till you will keep on eliminating these kind of terms and you will only be left with this. That is something that you have to notice. Then this lambda is there, this lambda is there, this minus is there, so it goes away. So it is 2 times, okay, 0 to infinity x. This lambda and lambda we have cancelled. We will write it out, e power of minus lambda x. This is what we are getting now. So, if you look at 2 times, see, this is what we want to find. But if there were a lambda, then I know what its value is. What is it? Here is the expectation. First of all, which is what that exercise we have carried out. So what I will do is I will divide it by 1 over lambda and then put so you get 2 by lambda square. Then variance of x. By lambda square minus 1 by lambda the whole square. Okay. So what? It is 1 over lambda square. So for exponential random variable, variance is 1 over lambda square. And sigma, what is it? Standard deviation. Is 1 over lambda. So it so happens that the mean is exactly equal to the standard deviation. And therefore what will be the coefficient of deviation? The 1. So that is certain all the important quantities of the exponentially distributed random variable. Well, then there are 2 other important things. One is this exponential random variable has a property called as the memoryless property. We saw the same kind of property with regard to the geometric random variable, and exponential distribution also has this property. What does it mean? In a common sense, what it means is, again I will give you the common example, that you know that if you stand in a taxi stand waiting for a taxi which may be coming anywhere from this city, but on the way if it comes you want to take the ride, so you are waiting. So if you ask some local person, he tells on the average within 10 minutes one taxi comes. So you just start waiting, 8 minutes has passed, it hasn't come. Now you ask what is the probability in the next 2 minutes it will come. The probability is not 1 because he said 10 and then you have waited for 8. It's not going to change. Again, the remaining time you have to wait will not have any bearing of how much time you have waited. You know that in the case of coin tossing it is very correct. How many failures has occurred will not dictate the future successes. That's very clear because each one is independent. Now this one is sometimes difficult to interpret. Okay? Even waited for 1 hour, the remaining time you have to wait for the event to occur, it still has the original distribution. It is independent of this. It's what exponentially. Sometimes it is maybe difficult to interpret, okay, but this has a very, it's obeyed in many properties where each time again the arrival of taxis are dependent upon the so many other people who has their requirement and so on. That is one thing. The lifetime of a component also. You start using a bulb, okay, it has worked for you at the beginning, you know that probability that it will work for 1 year, okay, up to 1 year, probability it will work up to 3 years. Everything you compute it and keep in the table. Now you have been watching it, it has worked for 2 years. Now you are wondering, if I start recomputing the probability that it will work for 1 more year, 2 more years, how it will be? And this, if you model the lifetime as an exponential distribution, the remaining lifetime will have the same distribution of the original lifetime. Okay, so that is what it is. Maybe for a lifetime of component you may wonder, no, it's not a very good way of this one, but many physical phenomena can be reasonably well modeled using exponential distribution. So what does it mean? That x is a expo random variable with the parameter lambda. Then you know that probability x is not probability, you know that x is greater than a value yes. It is a condition that is given. You have observed till yes and it has not failed, so you know x is greater than yes. Now you want to find the probability that x is greater than some more time. Okay, it will live for t more time units. That is what we want to find. Which means that the original lifetime of the x will be s plus t. If it has to survive for t more time, already it has survived till yes. So that will be s plus t, where t is the remaining lifetime or the residual lifetime, given that x is greater than s. This is what we want to compute. Given that it has survived till s, what is the probability that it will survive till s plus t? That is one way of telling. It will survive till s plus t is the same as the remaining lifetime is more than t. But both are one and the same. If I call the remaining lifetime as y, which is equal to s plus x equal to s plus y. X is the original lifetime, y is the remaining lifetime after surviving s. So you want to characterize this y. Well, so this is the same as the remaining lifetime greater than t. Both are one and the same. This statement again given this condition. Well, how do we find out this? So that is the same thing. Probability of a given b. The same thing you have to use. Probability of x is greater than s plus t and x is greater than s divided by probability that x is greater than s. This is what we have to do. Now these probabilities are something you want to find out. Now look at this one. There are two statements here. Both has to be satisfied. But one is a stronger statement. If that statement is obeyed, the other one is automatically obeyed. Right? Yes, t are all positive values. It cannot be negative. So this tells that x has to be greater than x. This tells that x has to be greater than s plus t, where t is some quantity. Maybe 0 or something. If this is obeyed, this is automatically obeyed. So it is, this condition implies this. So we can write it as probability that x is greater than s plus t divided by probability that x is greater than s. Now this is what we want to compute. So what we have so far computed is, we know if the CDF of this one, fx of x is known, and what is this property that x is less than or equal to x for an exponential random variable, that you know it as 1 minus e power of minus lambda x. I will use, this is very important, and we will frequently use this formula, so we can as well give due respect for it. So fx of x is property that x is less than or equal to x, but we are looking for property that x is greater than x. That can be written as 1 minus probability that x is less than or equal to x. The reason these two are this and this condition are mutually exclusive, collectively exempt. X can be less than x can be less than or equal to x, or it can be greater than x. There is no other way. So their probabilities has to add up. To take this one, their probability add up to 1. So this has to be true. And we know the formula for this. This is nothing but 1 minus fx of x. So again plug in fx of x formula for this one, 1 minus e power minus lambda. It's all for x greater than or equal to 0. So that gives you what? E power of minus lambda. That's it. This is true for x greater than or equal to 0, 0 of x. So this function is given by this. And this function will be of use, okay, in dealing with many problems. And what this function is, it is complementary to this CD. Okay, because it is 1 minus CD. So we will call this as the complementary cumulative distribution function. Okay. So in short, CCDF is the abbreviation we will use. So that is given by this. Now we will go back to the original one. So this quantity is given by probability x is greater than this, probability x is this one. This is nothing but the CCDF. But we have to evaluate at s plus t here. You have to evaluate at s plus s. That is given by e power of minus lambda into that quantity, because it is e power of minus lambda into s plus t. This is e power of minus lambda. Yes. So you can see that it is nothing but e power of minus lambda. So what we are getting is probability that y is greater than t, the remaining time y is greater than t, given this condition, has this form. So what is this one? This is the CCDF of y. Conditional C. I have to put one more C. Okay. Conditional complementary cumulative distribution function of y. That is as this form. So what will be the form of CDF of y? It has to be 1 minus this. So CDF of y. What is the property that y is less than or equal to small y? Will be 1 minus this. Okay. Now we have been calling this as t. Okay. Y I will put t itself. Is 1 minus e power minus lambda t. And what will be the, this is what Fy of evaluated at t is 1 minus e power minus lambda t. And what will be the density function? See, if this is of this form, density function will take the usual form of this one. lambda e power minus lambda x. Fy of t is lambda e power minus lambda t, which means that the remaining lifetime of the component is also exponentially distributed. The original lifetime of the component is exponentially distributed. You have waited for some time and then looking for the remaining lifetime, that is also exponentially distributed. But that is not a surprising thing. With the same parameter, it also has got the same parameter lambda. Now if you at that time, after waiting for yes and then finding that the component does not fail, now you ask what is the expected lifetime, remaining lifetime. That is also same 5 years. So to begin with, the expected lifetime of the component is 5 years. You have waited for 3 years, it has not failed. Now you compute the probability distribution is same. So exponent, variation, exponent, expected variation, everything will be same. So now you ask what is the expected remaining lifetime. That is why 5 years. You wait for 4 years, it does not fail. Now you again ask what is the expected lifetime of the remaining one. Again it is 5 years. So it goes like that, which means that a component, given that it has not failed, is as new as the original component. It has not aged. That is what it is we will tell. So it is like, I don't know, in your Indian mythology you will have someone called Markandeya who will never age. Its exponential distribution is something like that. It will never age. Okay? So that is the beauty or advantage of this one. Well, in many cases, yes, this is how it is obeyed. Some cases you may wonder whether it is a good way of modeling and so on, but the best thing is that because it makes the mathematics very tractable. That is the most important thing. There is one more nice connection between the let me just check whether I can take it in 2-3 minutes, whether I will be able to do that one. Connection between the geometric random variable and the exponential random variable. So what is the, we know that probability that x equal to k, where it is geometric. I will put x geo, k. What is it? It is p into 1 minus p power k minus 1. See, is a x, geometric is a discrete valued random variable. What does mean? Probability that you get the success for the first time in the kth trial is p into 1 minus p power k minus 1. P is the probability of success, 1 minus p is the probability of failure, k minus 1 failures, probability 1 followed by 1 success. This is how we will write it. Okay. And what is the probability that x is greater than k? That okay, less than or equal to k. If you try to put it, that then it is sigma k where x is greater than or equal to less than or equal to n. If you want to put it, x is equal to 1 to n e into 1 minus p power k minus 1. So what will happen? This one is 1 minus of 1 minus p power n minus 1 divided by 1 minus of 1 minus p. So this and this goes away. 1 minus of 1 minus p power it's not n minus 1. It is actually k is equal to, okay, whatever this is, and so on. Or n or it is n, is it? R plus 1, right? For a very large n, it is not going to matter. So this is how the CDF of geometric distribution random variable looks like. We are not derived so far incidentally that one. What is the, this is the probability that x is less than or equal to k, where k are all integral values. For an exposed random variable, probability that x is less than or equal to x is 1 minus e power minus lambda x. See, look at the similarity of these two formulas. Okay, so what? It looks like this 1 is there, minus is there, this term, and there is something very similar to this. So what it will do is, if we put that this x is the continuous valued random variable indicating the lifetime, I will divide into small time slices of 1 second or 1 minute each. Okay, and then let us say there are n such seconds in this time of 1 year or whatever it is, with this one. Each time slice being delta, x equal to n delta. So I can write it as 1 minus e power of minus lambda into n into delta power n. So this is how I can write it. So this 1 minus p is similar to e power of minus lambda. 1 minus p is very similar to e power of minus lambda. So if you ask the what it means, what is 1 minus p? P is the probability of success. 1 minus p is the probability of failure, means that event does not occur in the small time interval. That is what 1 minus p is. And this quantity, if you look at this one, this is the this is to be interpreted as what? Is the probability that the event has not occurred in this small interval for exponential random. So these two random variables are very, I have close connection. So we will stop at this.